Okay, welcome back to day 2 of the final presentations in observational astronomical instrumentation and multi-wavelength astrophysics. On this day, the first speaker is Derek Cabone, who's going to be talking about NGC 660.
Hello, good afternoon. My name is Derek Cabone, and today I will be talking about modeling the disk rotation curve in a polar ring galaxy. Here's the object we'll be looking at today. It's NG660, and it is a polar ring galaxy. As you can see, there's a prominent ring structure that extends around the disk, and it lies in a plane nearly orthogonal and rotates around the disk. What I will be looking at today is that this most likely occurred from an interaction with a nearby galaxy and pulled this matter in tidal stripping. But what we notice is that the disk looks intact. It doesn't seem too different. No warping or anything like that. So what's changed about this? Why is there this matter that goes around it, and yet it doesn't seem to have too much of an effect on the optical extent of it? What I'll be looking at is H alpha emission from the disk, and building a rotation curve, and seeing what we can say about the mass of the disk, and if this is different from what we would do for a normal spiral galaxy with the ring around it. As I've said here, we're looking at the kinematic characteristics of the disk and comparing it to a normal one, a normal spiral disk. The data that I looked at was observed on October 16th, 1991. It's kind of old, but it was what was available. It used the 1.52 meter telescope at Lucia, which is now decommissioned. They used a Bollins and Chivins shell grating with a blaze angle of 22.2 degrees, centered on 587 nanometers with a range of 200 nanometers. We'll be looking at H alpha emission, which is around 656. And in conjunction with the CCD they used, they 1 pixel corresponded to about 0.99 angstroms, so they had a spectral resolution of 2.2 angstroms. Now the data I received had already been reduced. They used the Munich Imaging Data Analysis System. And then they applied a Gaussian distribution to it. Now since the data I received was already reduced, I didn't have a chance to be too macho and do it myself, but we will trust they did all right. The axis that they looked at had a position angle of 55 degrees. The major axis of the disk is at 45 degrees, and this will come into some geometry later. So here's the data I got. As you can see, with the Gaussian distribution, they claim that they increase the resolution by a factor of 10, so much better. And as you can see, the H alpha emission is at 658.2 nanometers instead of 656. So it is moving away from us at about 650 kilometers per second. And now from this data here, we're just going to use the Doppler shift to get the line of sight velocity. As you can see, there's this bunch of data here that kind of stands out. It's a polar ring galaxy, so this is H alpha emission from the polar ring. And we're just going to be looking at the disk today, so we're going to ignore that from now on. And as you can see, I've written Doppler shift to get the line of sight velocity as a function of r, the radius, I, the inclination, and phi the galactic azimuth. That means that we're going to use some geometry. So the disk major axis at 45 degrees here, and what they looked at was at 55 degrees. So we're looking 10 degrees off the major axis on the projection of the galaxy. And since this is the case, that means that we're not seeing all of the velocity in the rotation curve, because some of the velocity is going to be going this way. Yes?
Which way is the positive radial coordinate on your previous plot?
Positive radial coordinate will be going this way.
That way.
Yes.
Okay, so the negative radial coordinate is in the upper right
Up here?
hand quadrant.
Yes. And there's where the polar ring galaxy comes across the disk.
And could you actually go to the previous slide? I just
Yes.
want to look at that. Maybe I missed this. What does the red mean?
The red means that this is the data that corresponds to H alpha emission in the polar ring. And we're going to be ignoring that since I was just going to be doing the rotation here for the disk.
Do you think that's from material in the polar ring?
Yes. Or the peak will be caused by the emission from the polar ring, but if you look at it, would be like widely dispersed because there's also H alpha emission from the disk behind it.
So it's confused, it's all together.
Yeah, but the peak should correspond to the polar ring itself, because that's where the route would come from because of extinction from gas. Any other questions so far?
Did you look at NED to find data sets?
Yes, but they didn't have as you can see, I have like 99 data points here, and that only had like 10 spectrum total. And most of them were of the center of the galaxy.
Right. So this is ideally suited to do the thing that you're trying to do.
Yes, many points along a certain radius, certain angle. So as I was saying, since we're off the major axis, then not all of the rotation velocity will be coming directly at us. Some will be going over here, some will be going over there. And since it's inclined, same thing applies. Some will be going up and some will be going down. So we're going to have to correct for this. So as you can see here, by the circle, we're making an assumption that the disk is a circle and that all of the velocity will be going into rotational velocity. Now, the inclination can be found by the cosine of the apparent minor axis over the apparent major axis, which is 71 degrees. And then to find the location of the galactic azimuth, we can just check and make sure it's right here. So we're looking for the inverse tan of y over x. We have tan of theta, we have h over x. And if we cos of I, this angle in here is also I, and that will be h over y. So this comes out to y over x, and then the inverse tan will go side 5. So the galactic azimuth we looked at is 28.44 degrees above the major axis, and going this way would have to be negative, or 180 less than. So this is our line of sight velocity, and this is the systemic velocity, which is how far the entire galaxy is moving away from us. And this will be the true rotation times the correcting factors for how much is actually coming at us due to inclination and galactic azimuth. Theoretically, at a radius of 0, the rotation will be 0. So if we find our line of sight velocity at r equals 0, we'll have our systemic velocity. And doing a little Lagrange interpolation polynomial, we find that approximately 863 kilometers per second away from us, which I checked with Ned is pretty rough estimate of our distance, how far away it is from us, using the Hubble law. And we see that it's about 12 3/4 megaparsecs. And that says it's about 13 megaparsecs. So that's good. And with this distance, this allows us to find a true radius, how far away from the center it actually is, and not just the projection that we see. And we're simply going to invert this top equation to find a true rotation. So here's our rotation curve. Looks pretty good. It comes up, flattens out, as we would expect. Along the center here, starts to decrease a little bit.
So did you fold the positive and negative data on top of each other?
Yeah, I took the radius, which is a positive, assumed to be positive.
Oh, right. Right, okay.
Yeah, so it's just distance away. So that includes the, so out here we'll have more points, and in here we'll have a few more points, because we took out a little section in the middle here. And this is just missing data. It has nothing to do with what we took out. So I did a quick math estimate, assuming that the gravitational potential energy was counteracted by solely the centrifugal force, so less pressure. But it gives us a rough estimate of the mass of the disk. As you can see, it starts to level off, so it's on the order of 10 to the 10th solar masses. So we will use this with an exponential rotation curve model, which is used in lots of spiral disk galaxies. And you'll see how this compares to our derived rotation curve. Doesn't do so good near the nucleus, which it never does. So that's our end. As you can see here, our rotation curve drops off a little bit more than this does. So something's a little different. So I'm going to introduce a new model, not new as to recent. It's actually 1960. It's called the RAT model. The RAT model parameterization of the rotation curve based on where it peaks and how it peaks. Now, this rotation curve was derived with the assumption that after the optical limit, it would fall off as a Keplerian rate, which is 1 over the square root of r. As you can see, matches pretty good up here. Goes through here, and then comes down roughly at what we derived. Now, there's something wrong with the Brandt model. It was derived to characterize highly flattened galaxies, but it made the assumption that it fell off with 1 over r squared after the optical limit, which in most galaxies is not true. It was like 10 years later, it was shown with radio observations that it stayed roughly flat. The rotation curve does. But in our case, we see that it does fall off. So that's different. So why might this happen instead of staying flat as other galaxies? Well, if you go out along the axis of the disk, where the disk plane intersects the ring plane, you would imagine that as you get closer and closer to the ring, the rotation in the disk plane would start to drop off as the rotation in the ring plane would start to increase. So this can account for that. But we didn't look at anywhere near the ring. We looked nearly orthogonal to it. So why is it going down up there? Not exactly sure. radio observations to see if it does go down as expected with the previous model. And I would also like to look at the same emission in the polar ring and combine the kinematics to get a three-dimensional picture of the kinematics. And let's see what we can say from this. But one other thing I skipped over here is that if we assume that the rest of this drops off approximately with the Brand model, then we can get the disk mass, which is roughly 10 to the 10th solar masses, which is close to what we saw with the Keplerian model. But is this truly what's there? Or is this all that we can determine from the rotation curve, since it will go to 0 eventually? Well, we have to look in the other plane to determine how much mass is below that radius. So is this truly a finite mass, or is this just a limit on what we can determine from the observations? Any thoughts?
Is it?
Yeah.
Okay, so we have time for questions.
It looks like the Brandt model is supposed to peak at around like just below 1 of R max, whereas the data points actually go in the other direction. Is that, you know, the signature of the Brandt model being wrong?
Well, what I noticed was that there was this periodic peaking and dipping. I'm not sure where that came from. It was actually way back in the email of mission peak 2. So I'm not sure why this is. I just assumed that it would continue flat. But my guess was this was the location of the spiral arms. And there would be a higher velocity dispersion in there, which would.
So it looks like there's some sinusoidal thing superimposed on it.
Yeah. I'm not exactly sure with that. Do you have an answer?
No, I'm trying to remember the typical rotation curve looks to be flat, right,
Yes.
for most galaxies.
Yeah.
And that's like saying that all materials co-rotating. Is that the one way to say it?
Yeah.
It's locked in. The velocity is the same versus
Velocity
radius,
is the same,
right?
so there's a differential.
So there's differential rotation if the velocity is the same.
Yes, because the other will fall behind.
Yeah. So in this case, this is a deviation from that,
Yes.
and it's differential rotation. It's somehow different than differential. It's I don't know why that is.
Yeah.
Is it seen in other systems?
I don't know.
Could you go back to slide 3? Yeah.
Okay.
What's the answer to question 1?
It would be supposedly yes. I didn't make a firm conclusion, but we saw that it did drop off, which is different from normal spiral galaxy. The rotation curve.
So the drop off at the end
Yes.
is different, and one reason to be suspicious about your conclusion perhaps is because it's just a handful of data points.
You can only see so far.
Yeah,
And the model I chose was designed such that it dropped off.
what's the answer to question 2?
Question 2 is that we can make a finite estimate of the mass, because eventually.
Well,
rotation will
question,
be-
I think both of these questions require an answer yes or no.
Right.
So in 1, it was yes, comma, maybe, I think. And then 2, is it yes or no?
It's a yes comment. Because we can only, my conclusion was that since it dropped, the rotation curve dropped off, we can only determine so much mass from the disk. It's a limit on how much mass we can determine from the disk. So it's not necessarily is the distribution different, it's what we can determine from the rotation of the disk.
So the drop off would imply less enclosed mass
Yes.
at the outermost radii
Yes.
than data points from more in the middle, let's say. Is that what your plot showed? It was a drop off and implied, because if you go to the mass plot, it looked like it dropped off at the end. So this, when you have mass on the y-axis,
Yes.
that is implied encircled mass or enclosed mass.
Yes,
right?
within that radius.
Right, and your implied mass for the outermost data points is less than
That
the
was before.
implied mass for the points in less radius, right?
Yes. And this is, when I read about the Brandt model, he started by saying that this specifically was a flaw of the Chandrasekhar and Coplarian rotation models, where after a certain radius, you would see a negative mass. And his model supposedly corrected for that, where it would go up slower and then reach a limit.
Now, when you invert the velocity into mass,
Yes.
you assume a certain distribution, spatial distribution, and velocity distribution for the mass, right? And it could be that those assumptions are not as true for the outermost material, right? So your computation infers the wrong mass, enclosed mass. Could you go back to slide 2? Could you point at the ring, sort of move your finger around the ring? Okay. Is it possible to measure the velocity of H alpha in the ring?
Yes, it is. But it was a little more difficult because the ring is warped. So the data that I had, it is, the ring itself is inclined 55 degrees on average to the spiral disk plane. And when I worked out the geometry for that, I got velocities that were all over the place.
So someone laid down a slit along the ring?
Oh, I thought you meant the data that I had.
No, is it, more generally, is it possible to measure the velocities?
Yes.
Has someone done that?
Yes, I have.
Is it interesting? Does it relate to your questions?
I believe yes, it does, and that it shows that its velocity is lower in the polar ring, and it also comes up in the peaks, and then stays there.
What, could you summarize the work that's been done, let's say, on this object in regards to the questions you're asking? Like maybe someone's thought about this or they've talked about this before. Did you find papers?
Yeah, I can refer you to one.
And
I just,
could you go to slide 3 again? I just want to look at the questions again. Or maybe even other objects. Maybe not exactly this object, but other polar ring systems. Have people detected signatures of something different in those things?
I know that they use the same rotation curve models to determine mass for certain parts of it.
I see. And did you notice any drop off, or I guess you didn't notice the sinusoidal pattern that was?
They didn't have the sinusoidal pattern and they didn't have the drop off. They always had it continuous and steady.
So I guess if you were to extend this, you might try to get a sample of systems and repeat a similar analysis and then try to figure out, what are the characteristics that are unique to the polar ring systems, right? As opposed to other galaxies. Okay, any other questions? Okay, let's thank Derek.